Hi, my name is Radu Teodorescu. I'm working for data technology at WorldQuant, and I've been a big data nerd for a very long time now. The main gist behind this presentation is to talk about the challenges that we have encountered historically in the big data finance, trying to adopt mainstream open source and commercial solutions. As far as kind of the way my conversation is going to go, I'm going to first start by providing the success story. We've been, finally, after many years of trying to get it right, at WorldQuant, after joining WorldQuant, I have been able to deliver a successful data lake solution based on Apache Archer. And then I'm going to take you back in time and go over the historical challenges that we have been encountering reconciling the open source big data technologies with the needs of quantitative finance, and cover the main topics and look at ways in which we can continue to bring the two worlds together. First of all, I just want to start with the happy ending of our story. In the past, I have gone through many iterations of building large-scale data storage and analytics for different financial companies. Oftentimes, we build them from scratch. We had, different experiments with different types of open source technologies. In the case of after joining WorldQuant about 2 years ago, the focus has been trying to leverage Apache Archer as the base for our technology. And I'm happy to report that we managed to have a very successful and rapid development cycle. And I can probably safely say that it's been kind of the fastest moving project that I've had the opportunity to be involved on. And just here to kind of give you a couple main points of the timeline. So I joined WorldQuant less than 2 years ago in July of 2020. Within kind of the first month, looking at the data needs of the company, I sketched out a proposal for how a data lake solution can look like that would be scalable and give us all the flexibility that such a financial firm would need. We managed to actually put, and by we, I think it's been initially just me, I managed to put a POC together within less than a month. Managed to move from POC to the first minimum viable product with the initial real-life user testers within another 2 months. Another 4 months, so basically about 6 months from startup, we had the actual official production launch for the entire company. And things kept on moving really fast from that point onwards. About a year ago, we started adding a couple more developers to the team. We managed to move the product from being kind of like a monolithic single server to a distributed server solely through the effort of an intern. So that was actually a really major achievement, effectively something that typically would take many, many months for professional developers. You managed to have very smart, but just an intern scaling the product from being a single server to being a distributed architecture. Less than 2 years from moment zero, we have a fully functional data lake product that is central to the data growth strategy in WorldQuant. It's running on over 50 servers. It's storing more than 10,000 tables. Some of the tables have north of 1 trillion rows. The system on a daily basis is serving over 200 billion rows, more than 10 terabytes of compressed data. It's ingesting over 5 billion rows and adding about 10 gigabytes of data, again compressed on a daily basis. And we're just getting started, so we expect this rate to continue to go up. So as I said, things haven't always been that easy, and I'd like to kind of go back over some of the challenges we have encountered historically, addressing big data problems in finance tech, and kind of understand why off-the-shelf solutions haven't always served the needs of this industry sector. So first of all, the problem is that historically, and by historic I mean really going back 10, 15 years ago, data in finance has been tended a lot larger than the big data that company have been dealing with. So it was pretty common for a small company of say 50 to 100 people to have to deal with storing upwards of a terabyte of data per day, and keeping close to petabyte in their own storage, which is not something that was typical for small tech companies outside of finance. So big data was to some extent was a problem before the big data was an actual buzzword. The access patterns in quantitative finance tend to be quite different, and I'm going to go into more details on that. Then, what are the typical access patterns in a company like say Google or Twitter, and also historically, financial world has been quite suspicious of the open source space. So there's been very little cross-pollination. So the needs of the finance technology world haven't necessarily been written in open source, partially because people in this space haven't been very much involved in that area. As I said, I have been a late adopter of the open source trend. I've always been quite suspicious of the solutions that I haven't built myself. And Apache made me a bit of a convert, so I'm just going to kind of go through a little bit of my journey getting here. So one of the first barrier for adopting a third-party platform is the not built here syndrome, and it's both psychological. Especially when you have a group of elite developers, they tend to think they know better. Most of the time, they do know better, especially their specific problem space. And there's a general, sense in all of us that we can actually do a better job than anybody else out there. But on the flip side, there are some real objective things to be considered. So first of all, on the upside, if the solution is out there, it's silly not to use it. So, and this is definitely something that especially as you look down as a manager, or as you look at a team, you don't want your team to reinvent the wheel. So that's definitely a big consideration. On the flip side, historically, there have been a number of misusages of available data storage solutions. And generally what happens is when you adopt a product, you run through a couple of benchmark, couple of tests, everything looks good. And it just so happens that within 6 months of adoption, things start breaking, and it becomes very hard at that point to either roll back because you only make a big investment and you have a lot of infrastructure depending on it. But in the same time, it often becomes very hard to troubleshoot that platform. So yes, you get a fast start, but on the flip side, you find yourself having to maintain a product that you don't fully understand. And in our world, people are actually very good at pushing the boundaries of any system out there, and having the ability to actually understand things down to the intimate details is somewhat key to being successful. So looking at how Apache Arrow has addressed this problem, or how it helped me overcome this problem. So first of all, Apache Arrow doesn't give you a monolithic product, and I think that has been key to its success. It just gives you a set of libraries that are highly interoperable with existing off-the-shelf solutions, and you effectively have a set of Lego bricks. You get to pick and choose what you want to use, and as a developer and as somebody running a development team, you are still in control of the product that you're developing. The second part that actually made the adoption easy, the code is highly readable. I mean, documentation is great, but oftentimes it's actually really easy to kind of dive into the code, understand kind of what's going on, get a good sense of the semantics. The approach seemed very familiar for anybody who has built, a big data system in my world. So just a lot of kind of attention to details, fine-tuning, allocation, staying close to the metal, all those things, they seem like they're in the right place. So just kind of going through the system, it looked like, okay, this looks very much like, well, it's like something that I've built in the past or something that I should have built. And last but not least, there is a very active community around it, which has been very helpful. I mean, the community is extremely responsive. We can always engage in there. And to my surprise, WorldQuant also had a number of enthusiastic members of the community. Some of them actually active members of the community, others just excited about the Apache Archer prospect. So it made it easy for me to bring the product to the company because there was already enough critical mass here to actually promote it and get support in that space. Next big challenge for adopting traditional big data solutions comes down to the access pattern. So especially if we go a little bit back in time, back to kind of the early days of Google, the MapReduce model, the whole big data approach was based on a model where there's a very large number of users, each and every one of those users expecting a small amount of data, right? We run a query on Google, you receive a small result. We just want to be able to serve that thing to billions of people. So the whole trivially parallelizable, broadly MapReduce, linearly scalable approach makes a lot of sense in that space. And that was there were some of the early developments in the big data space. On the flip side, in quant finance, you have to deal with a small number of users that actually have very high data expectations. So oftentimes, problems are not that trivially parallelizable. You need to actually run large queries, deliver large data sets from an even larger data sets to a limited number of very demanding users. So looking at how this problem is being mitigated by Arrow, what makes Arrow appealing in this space. First of all, it is built with big data set in mind, not only in terms of storage, but in terms of everything on the stack. So transport, in-memory representation, everything is designed to actually allow you to handle as much data as your native hardware allows you to. It is, sequential performance is a big consideration in there. So it actually allows you to kind of do things sequentially at speed, as opposed to, we have to MapReduce this thing over a bunch of nodes. Low to zero serialization cost is also kind of another big factor in here, which is allowing you to move large amounts of data. And overall, performance tends to be very close to the hardware limits. Memory access time is tied into the Arrow model, which Arrow array model, which are effectively in-memory buffers for most implementations. The limit again is being pushed. Both Parquet and Feathers allow you to pretty much get IO's throughput that it's on par with what your underlying storage allows you to. And similarly, Arrow Flight is bound by the network bandwidth, not by the serialization cost. So all these things kind of allow you to move large amounts of data and deliver them to small number of users. The second big distinction in there is kind of the dichotomy between vectors and sets. So I tend to like to say that quants think in terms of vectors, and you can think that kind of conceptually of everything linear algebra, while databases talk in sets. And I know this is some can argue that this is a somewhat a bit of an exaggeration, but conceptually in finance and in kind of quantitative research, data is viewed conceptually as deterministically ordered. You have a time series of data, you have ticks from exchanges, etc. You expect this data to be indexable in constant time, and you expect to be trivially copyable. You want to be able to kind of move buffers of data around. And this is kind of the natural way in which most of the successful products in the quantitative finance have worked. On the flip side, in the database world, there are two models. You have the traditional SQL model, where data is conceptually thought of as a set. I mean, obviously you can order it, but this is like an afterthought. Or in the NoSQL space, again, grossly generalizing, but the overarching model for the data is that of a map. So bringing those two things together ends up kind of causing some friction and leading to less than optimal solutions. As the canonical example for, and it's usually used like the biggest gotcha for testing any big data product when it comes to finance, there is the Azov join operation. So for those who are not familiar, the idea behind an Azov join is it's similar to a traditional join, except that the matching is a temporal match, is not an exact match. So to give an example here, you want to find out what was the market bid and ask at the time when a trade happened. So on the left side, you say you have a trade for VOD that happened 1202, and you want to know what does the market say at that point. So the match requires to do an exact match on the symbol, so it's going to be VOD to VOD, but the time is going to be the greatest, or the time that is greatest or equal to the time of my trade. So it's not an exact time on the exact match on the time. It is it is a relative match. This type of construct has been added to pandas a while back, and it's generally not supporting by most of the SQL products. And apart from the support itself, it's just very awkward to express if you're thinking of data in terms of an actual set. And it's both, it can be done obviously, but it's a lot easier to model both conceptually and also implementation wise if you think of the data as an actual order vector. So back to Apache Arrow. One of the things that made me very excited about is that everything is kind of built around the concept of array. So we're not dealing with kind of abstractly ordered data sets. Everything has a very, very deterministic order. These arrays, as I mentioned earlier, they are native, they are close to the metal, so they expect to behave as fast as your underlying machine does. And I hear from the grapevine that Azov join is in the making right now, so I'm actually very excited to see it coming to Arrow. Okay. Also, somewhat related, just a different side of this in terms of kind of relation between a traditional database and the compute process in quantitative analytics. If you look at how databases have worked, the typical use case has been like you have the database, you have a server back end, and you have a user front end. And there's a very clear engineering separation between these stages. It makes perfect sense to have different languages for each and every one of them, because each and every one of them is kind of a isolated abstraction. And having separate language almost makes it easier to keep these things nicely encapsulated. On a quantitative analytics and generally any data analytics, big data analytics process, the data flow is not as clear cut. So typically you have this circular query compute loop where you ask for some data from your storage, you apply some computation, transformation, regressions, whatever. Based on those results, you ask for more data and so forth. In this case, having data query language and data provider as a separate entity, both language-wise and typically a physical entity as well, from your compute space is nothing but a hindrance. It makes the actual code a lot more complicated, and at the same time, it also leads to a lot of unnecessary data transfers between the two different layers of. Looking at kind of the promises of Arrow in this space. First of all, Arrow provides your library, doesn't provide your client-server architecture. So it is somewhat down to the user to decide where the client-server boundary exists, and if the query engine then can be collocated with the compute. If the data and query engine need to be collocated with the compute, that can easily be done. User-defined computation can definitely exist. Can have data both the query engine and the compute can be applied to the same data in memory without having to move anything around. And I know that there are ongoing efforts to allow for better UDFs and query primitive integration. So just very excited about that perspective. Another problem that somewhat has been challenging the specific use cases in quantitative finance has been related to data velocity. So in reality, when we talk about big data, there are actually three types of bigness. There's a big data storage, and that has been the space that has been typically associated with a big data problem. But there are also issues that have to do with high throughput for live data and low latency data. And in a typical, quant finance application, you want to be able to address all three aspects from the same type of application, same container. So, typically you want to do some historical analysis, look at a lot of historical data recorded, come up with some strategy, test them, and then you want to have that exact same strategy, same code container run against live data. So your live data needs to run against a live stream and needs to run against a table. Traditionally, dealing with streams and dealing with tables and storage has been addressed by different products because in the world outside, those things tend to actually be segregated problem spaces. So trying to find a unifying abstraction with the existing tools has been challenging. The challenge hasn't completely gone away there. I think it's still, it's still something to be explored. But as far as kind of the promises, Aeroflight does allow, and I've been successful in using Aeroflight to deliver live data as a batch stream. So it's still not going to deliver data, record by record. Is going to deliver it in batches, but with that we can actually achieve pretty high throughput and manageable latencies in data streaming. The serialization costs are really low, so that means that you can actually deal with extra hops easily. You don't have the challenge of storing data in a database and having to fetch it right away, where it's either going to be slow or you're going to really force the indexing engine under the hood. As I said, this is not necessarily a problem that has been kind of a central focus of the Arrow product. I think it's just the fact that we've been successfully using it in that space as kind of a testament to the architecture overall. But I think there are a lot of opportunities for further pushing Apache Arrow to accommodate live streaming and to provide kind of unified tools dealing with both static and live data. Okay, so this has been kind of my main points on the experience. As far as kind of the parting words, I think there are about kind of 4 overarching themes that I think are meaningful and just kind of my pleas for the community. I think keeping it modular, it's one of the key elements, and as I said, that has been sort of the entry point for the success. It's a lot easier to have a gradual adoption if you're dealing with a set of modules as opposed to having to onboard an entire ecosystem at once. I think keeping things close to kind of underlying machine performance, no matter how far we can scale things, just making sure that the single-threaded performance kind of stays there. I think that is key, and I think it's pretty much locked in stone already. The third point, I would just kind of like to kind of stick to one of my favorite pet peeves is that data science lives at the intersection of linear and relational algebra, and building proper unifying tools and abstractions that allow for both would be extremely powerful. I mean, Python Pandas has made some forays in that, and I would argue that the key success of Python Pandas is that we can do data manipulations and data science operations in the same space. And Arrow obviously gives us the opportunity to do that at a much larger scale in the past. And finally, I think trying to standardize and push further in terms of unifying streaming and storage abstractions. I know, making streams first-class citizens for things like Aeroflight. I think those would be things that would open a lot of interesting opportunities and save everybody a lot of bespoke work. So this has been my presentation. Unfortunately, this year I have the opportunity to interact directly, but I look forward to everybody's feedback and so thank you so much.